Everything you think you know about speed, light, and reality itself is about to shatter. Right now, at this very moment, light is traveling through your room at exactly 299,792,458 meters per second. Not approximately. Not around that speed. Exactly that speed. But here's what will make your brain hurt. A photon leaving the surface of the sun doesn't experience any time passing before it hits your eye. From the photon's perspective, its 93 million mile journey happens instantaneously. Zero time, zero distance. And somehow, impossibly, the universe enforces this cosmic speed limit with mathematical precision that makes our most accurate clocks look like broken sundials. But wait, it gets stranger. The speed of light isn't really about light at all. It's the speed of causality itself, the maximum rate at which cause and effect can propagate through reality. It's the speed of gravity, the speed of information, a fundamental tick rate of the universe. And here's the part that kept me awake for weeks. This speed limit isn't enforced by some cosmic police officer. It emerges from the geometric structure of spacetime itself. The universe doesn't know the speed of light any more than a triangle knows its angles must sum to 180 degrees. It's built into the fabric of existence. What if I told you that asking, how does the universe know the speed of light, is like asking, how does the universe know how to be a universe? The speed of light is so fundamental that without it, space and time themselves couldn't exist. Energy and mass would be meaningless concepts. Causality would break down. Reality as we understand it would simply not compute. Over the next 3.5 hours, we're going to journey through one of physics' most profound mysteries. We'll discover why light must travel at exactly the speed it does, why nothing can go faster, and what this reveals about the deepest nature of reality. By the end, you'll understand why Einstein called the constancy of light speed the most important fact in all of physics, and why some of the smartest people alive today believe this speed limit might be the key to understanding consciousness, quantum mechanics, and the origin of existence itself. Before we dive deeper, and trust me, we're about to go very deep, hit that like button and subscribe, because this is going to be a wild ride through concepts that most people never encounter. Drop a comment telling me what country you're watching from and what time it is right now. I'm genuinely curious how far across the globe this mind-bending conversation will reach. Are you watching this at 2 a.m. unable to sleep because physics questions haunt you? You're my people. Let's start with what seems like a simple question. What is speed? You're probably thinking it's distance divided by time, right? Miles per hour, meters per second. Simple stuff we learned in middle school. But that definition hides something absolutely profound that nobody tells you. When we say something moves at 60 miles per hour, we're secretly making an assumption that there's some universal clock ticking away, measuring time at the same rate for everyone, and some universal measuring stick defining what a mile means everywhere in the universe. For thousands of years, this seemed obviously true. Time was time. Space was space. They were the stage on which the cosmic play unfolded, but they weren't part of the action themselves. Then came a problem. A really, really big problem that scientists in the late 1800s couldn't ignore anymore. Light was weird. Astronomers had known for centuries that light traveled fast, but not infinitely fast. In 1676, a Danish astronomer named Ole Reckner made the first real measurement of light speed by observing the moons of Jupiter. He noticed that when Earth was moving toward Jupiter, the eclipses of Jupiter's moons appeared to happen earlier than predicted. When Earth moved away, they appeared late. The discrepancy wasn't because the moons were unreliable. It was because light took time to travel the changing distance between Earth and Jupiter. Reckner calculated light traveled at about 220,000 kilometers per second. Not bad for the 17th century. By the mid-1800s, scientists had measured light speed to incredible precision. They knew it traveled at approximately 300,000 kilometers per second. But here's what bothered them. Speed relative to what? When you say a car moves at 60 miles per hour, you mean relative to the ground. When you say Earth orbits the Sun at 67,000 miles per hour, you mean relative to the Sun. So when light travels at 300,000 kilometers per second, relative to what is it moving? Scientists thought they had the answer: the luminiferous ether. Think of it like this: sound waves travel through air. Water waves travel through water. So light waves must travel through ... something. They imagined space was filled with an invisible, weightless substance called the ether, and light was vibrations in this cosmic medium. Light's speed of 300,000 kilometers per second would be its speed through the ether, just like sound speed through air is about 340 meters per second. This made perfect sense. Too much sense. It fit with everything scientists understood about waves. There was just one tiny problem. They couldn't find the ether anywhere. In 1887, two American scientists, Albert Michelson and Edward Morley, conducted what's often called the most famous failed experiment in history. Their logic was brilliant. If Earth is moving through the ether at 30 kilometers per second as it orbits the Sun, then light should appear to travel faster when Earth is moving with the ether wind and slower when moving against it. Just like you can run faster downwind than upwind. They built an incredibly sensitive device called an interferometer that could detect tiny differences in light speed. They measured light traveling in the direction of Earth's motion through space and light traveling perpendicular to it. They tested it at different times of day and different times of year, when Earth's velocity through the supposed ether would be different. The result? No difference. None whatsoever. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. It was as if they were running downwind and upwind at exactly the same speed, which should be impossible. Here's what will blow your mind. Imagine you're on a train moving at 100 miles per hour, and you throw a ball forward at 20 miles per hour relative to the train. Someone standing on the ground watching would measure the ball moving at 120 miles per hour, the train speed, plus the ball speed relative to the train. This is called velocity addition, and it's so obvious, we never think twice about it. But light doesn't work this way. If that train is moving at 100 miles per hour and you shine a flashlight forward, the light doesn't travel at the speed of light plus 100 miles per hour. It travels at exactly the speed of light. If you shine the flashlight backward, same thing, exactly the speed of light, not the speed of light minus 100 miles per hour. Light's speed is constant, regardless of the motion of the source or the observer. This violated every intuition about motion. It was like the universe was playing favorites with light, giving it special rules while everything else followed the common sense rules of velocity addition. Scientists scrambled for explanations. Maybe the ether got dragged along by Earth? Experiments disproved that. Maybe the measuring apparatus physically contracted in the direction of motion? That idea was getting warmer, but still didn't explain the deeper weirdness. Then in 1905, a 26-year-old patent clerk named Albert Einstein had an idea so radical, so counterintuitive, that it would overturn humanity's understanding of reality itself. He asked a simple question. What if light's speed being constant isn't the weird thing that needs explaining? What if light's speed being constant is the fundamental truth, and everything else, our concepts of space, time, motion, even simultaneity itself, what if all of that has to adjust to accommodate this one absolute fact? Einstein proposed two postulates for his special theory of relativity. First, the laws of physics are the same in all inertial reference frames. This means if you're moving at constant velocity, you can't tell you're moving. All the laws of physics work exactly the same. You've experienced this on a smooth airplane flight. When the plane isn't accelerating, you can't feel that you're moving at 500 miles per hour. You can pour coffee, throw a ball, and everything works exactly like it would on the ground. Second postulate. The speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This was the radical part. This was the assumption that seemed to violate common sense, but perfectly explained Michelson and Morley's results. From these two simple postulates, Einstein derived consequences that sound like science fiction. Time passes at different rates for people moving at different speeds. Objects contract in the direction of motion. Events that are simultaneous for one observer happen at different times for another. Mass and energy are equivalent. And the closer you get to light speed, the weirder everything becomes. But here's what most people miss. Einstein didn't just describe these effects mathematically. He explained why they must happen. If light speed is constant, then time and space themselves must be flexible, dynamic, and relative. They must bend and warp to ensure that no matter how you're moving, you always measure light at the same speed. Think of it like this. Imagine you and I are trying to meet at the corner of 5 meters away and 3 seconds from now in spacetime. If you're standing still and I'm moving relative to you, we're tilted with respect to each other in spacetime. My now is slanted compared to your now. My measurements of distance are squeezed compared to yours. And this is the crucial bit. These adjustments happen in exactly such a way that we both measure light traveling at the same speed. The universe isn't enforcing the speed limit. The geometry of spacetime makes any other result mathematically impossible. This raises the question we're really here to answer. Why this specific speed? Why 299,792,458 meters per second and not some other number? And more fundamentally, what is this speed a property of? Here's where things get really interesting. The speed of light isn't actually about light. Let me say that again, because it's crucial. The speed of light is not a property of light. It's a property of spacetime itself. We call it the speed of light only because light was the first thing we discovered that travels at this universal speed limit. But it's really the speed of causality, the maximum rate at which cause and effect, information, or influence can propagate through the universe. Anything with zero mass travels at this speed. Light does. Gravitational waves do. If we ever discover that neutrinos have exactly zero mass, they travel at precisely light speed too. The speed isn't caused by some property of electromagnetic waves or photons. The speed exists as a fundamental feature of spacetime, and massless things are simply obligated to move at that speed. They have no choice in the matter. But why this speed specifically? Why not twice as fast or half as fast? This question is about to take us somewhere unexpected, somewhere that connects the speed of light to the fundamental constants of nature and the structure of reality itself. But before we go there, let me leave you with a thought that should make you uncomfortable. In a very real sense, only massless particles like photons actually experience the true nature of spacetime. Everything else, including you, is being constantly accelerated away from light speed by the resistance your mass creates. We're all desperately trying to travel through spacetime at light speed, and only our mass holds us back. What does that mean? What would it mean to experience reality the way a photon does, where all distances are zero and all journeys instantaneous? We're about to find out, and the answer will change how you understand your place in the cosmos. Let's talk about what moving at light speed actually means, because here's where reality becomes genuinely strange. When you move faster through space, you move slower through time. This isn't a metaphor or an approximation. It's literally, physically true. Time slows down for you. If you could somehow accelerate to 90% of light speed and travel to a star 10 light years away, then return, you'd experience the journey taking about 9 years. But when you got home, everyone you knew would be 20 years older. At 99% of light speed, you'd experience only about 3 years, while 20 years passed on Earth. At 99.9% of light speed, you'd experience less than a year. Now, here's the kicker. As you approach light speed, time dilation becomes infinite. At exactly light speed, from your perspective, no time passes at all. 0. A photon of light leaving the Andromeda galaxy 2.5 million light-years away reaches your eye in what is, from the photon's perspective, literally the same instant it left. The photon doesn't experience those 2.5 million years. From its reference frame, it's created and destroyed at the same moment. This leads to a profound realization. Photons don't move through time. They move through space, all space, instantly, but they don't move through time at all. They exist on what physicists call null geodesics, paths through spacetime where the time component is 0. Think of it like this. You're constantly moving through spacetime at a fixed total speed. Call it the spacetime speed. When you're sitting still in space, all of your motion is through time. You're moving forward through time at the maximum rate. When you start moving through space, you're diverting some of your spacetime velocity from the time direction into spatial directions. The faster you move through space, the slower you move through time, because your total spacetime speed stays constant. Objects with mass can never reach light speed, because that would require diverting all of their spacetime velocity into spatial motion, leaving none for motion through time. It would require infinite energy. But massless particles have no choice. They must travel at light speed. They use all their spacetime velocity for spatial motion and none for temporal motion. Here's what this reveals. The speed of light isn't really a speed limit in the conventional sense. It's a conversion factor between space and time. It tells us how much space equals how much time. In natural units that physicists prefer, we often set the speed of light to 1, which makes this explicit. 1 second equals 299,792,458 meters. Space and time are measured in the same units because they're really the same thing, different aspects of spacetime. In 1908, Hermann Minkowski, who had been Einstein's mathematics professor, gave a lecture where he declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He formalized Einstein's relativity into a geometric theory of four-dimensional spacetime, where the speed of light plays the role of a geometric constant, the slope that separates time-light from space-light directions, the boundary between past and future light cones. This geometric view reveals something profound. Asking why the speed of light has the value it does is like asking why a circle has a ratio of circumference to diameter of pi. The value emerges from the geometry. The speed of light is built into the metric structure of spacetime, mathematical object that tells us how to measure distances and times. But we can go deeper, way deeper, because there's a more fundamental question. Where does this geometric structure come from? Why does spacetime have this particular metric? Why does it have this conversion factor between space and time rather than some other value? To answer this, we need to talk about James Clerk Maxwell, a Scottish physicist who, in the 1860s, unified electricity and magnetism into a single theoretical framework. Maxwell's equations describe how electric and magnetic fields interact and propagate. When Maxwell worked through the mathematics, something extraordinary fell out. His equations predicted the existence of electromagnetic waves that propagate through space. And crucially, the speed at which these waves propagate was determined by two fundamental constants: the permittivity of free space, epsilon, ebb, and the permeability of free space, mu ebb. These constants describe how electric and magnetic fields interact with empty space itself. The permittivity tells us how much electric field is generated by a given charge. The permeability tells us how much magnetic field is generated by a given current. When Maxwell calculated the speed of electromagnetic waves using these constants, specifically, the speed equals 1 divided by the square root of epsilon b dot, approximately 310,740,000 meters per second. Maxwell realized this was awfully close to the measured speed of light. In one of the great aha moments in physics history, he proposed that light itself is an electromagnetic wave. This was confirmed experimentally by Heinrich Hertz in 1887, who generated and detected electromagnetic waves in the radio frequency range, proving that electromagnetic radiation exists beyond visible light. But here's what this tells us. The speed of light is determined by how empty space responds to electric and magnetic fields. It's a property of the vacuum itself. The speed of light is really shorthand for the speed at which changes in fields propagate through the quantum vacuum. Now, in modern physics, we've learned that the vacuum isn't really empty. It's seething with quantum fluctuations, filled with virtual particles constantly popping in and out of existence. The quantum vacuum has properties, structure, even resistance to certain types of changes. The permittivity and permeability of space reflect this underlying structure. But wait, doesn't this sound suspiciously like that old ether theory? Yes and no. The quantum vacuum is real and has properties, but it's not some stationary medium that defines an absolute reference frame. It's Lorentz invariant, meaning it looks the same to all observers regardless of their motion. It doesn't violate relativity. It's consistent with it. The quantum vacuum is the modern understanding of the substrate of reality, and its properties determine fundamental constants like the speed of light. Here's where your brain should start to hurt. The speed of light is determined by the properties of empty space, but the properties of empty space are determined by quantum fields. And quantum fields are described by theories that assume the speed of light. We've got a kind of cosmic bootstrap problem. These fundamental features of reality all mutually define each other. The speed of light, the structure of spacetime, the properties of quantum fields. They form an interconnected web where changing any one piece would require changing everything. In 1999, physicist Joe Maguire and others proposed varying speed of light theories, asking whether the speed of light might have been different in the early universe. The math works, but it requires changing multiple fundamental constants in coordinated ways to avoid breaking the universe. This suggests that the speed of light isn't arbitrary. It's constrained by the requirement that reality must be self-consistent. Think about what this means. The universe knows the speed of light, the same way a mathematical theorem knows its proof. It's not that there's some mechanism enforcing the speed limit. It's that the speed limit is built into the axioms of reality. Change the speed of light, and you'd have to change the fine structure constant, the strength of electromagnetic interactions, probably the mass ratios of fundamental particles. You'd end up with a completely different universe, probably one where atoms couldn't form and chemistry couldn't exist. We're beginning to see that the speed of light isn't just a random number the universe picked. It's connected to everything else about how reality works. But there's an even deeper level to explore, one that takes us into the quantum realm where things get really weird. Because while relativity says nothing can go faster than light, quantum mechanics seems to suggest things can influence each other instantaneously across any distance. How do we reconcile these two pillars of modern physics? That contradiction between Einstein's speed limit and quantum entanglement's apparent instantaneous connection nearly broke physics in the 20th century. Understanding how it resolves will show us what the speed of light is really limiting and what it isn't. And that understanding will reveal something profound about the nature of information, reality, and the boundary between the possible and the impossible. Albert Einstein called it spooky action at a distance, and he hated it. He thought it proved that quantum mechanics was incomplete, that there must be some deeper theory we hadn't discovered yet. He was wrong about that, but his instinct to be troubled by quantum entanglement was absolutely justified, because entanglement seems to violate everything we just said about the speed of light being the cosmic speed limit. Here's the setup. Take two particles that interact and become entangled. Now separate them by any distance across the room. across the galaxy, doesn't matter. Quantum mechanics tells us that before you measure either particle, both exist in a superposition of states. Neither has a definite property yet. But the instant you measure one particle and it collapses into a specific state, the other particle instantaneously collapses into the corresponding correlated state. If you measure one electron's spin is up, the entangled partner instantly has spin down, no matter how far away it is. There's no signal traveling between them at light speed. The correlation is instantaneous. Einstein thought this was absurd. It seemed to allow faster-than-light influence, violating the cosmic speed limit. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper laying out this problem, now called the EPR paradox. They argued that quantum mechanics must be incomplete. There must be hidden variables properties the particles possessed all along that we just didn't know until we measured them. Like a pair of gloves in separate boxes, when you open one and find a left glove, you instantly know the other box contains a right glove, but there's no spooky action at a distance. The gloves had those properties all along. For decades, this seemed like a philosophical debate. Then in 1964, Irish physicist John Stuart Bell derived an ingenious mathematical test, now called Bell's inequality, that could distinguish between quantum entanglement and hidden variable theories. If hidden variables exist and particles have definite properties before measurement, then the statistical correlations between measurements must satisfy Bell's inequality. If quantum mechanics is right, and particles are truly in superposition until measured, the correlations would violate Bell's inequality. Experiments have been performed countless times with increasing sophistication. The results are unambiguous. Quantum mechanics is right. Bell's inequality is violated. The correlations are stronger than any hidden variable theory could produce. The particles genuinely don't have definite properties until measured, and yet they remain perfectly correlated across space. So what's going on? Are we allowing faster-than-light influence? Is the cosmic speed limit violated? Here's the subtle but crucial answer. No. And understanding why teaches us something profound about what the speed of light actually limits. The speed of light limits the transmission of information and causal influence. You can't use the speed of light limit to send a message or exert control. And here's the key. You can't use quantum entanglement to send information faster than light. Think about what happens in an entanglement experiment. Alice measures her particle and gets a random result, say, spin up. She now knows Bob's particle is spin down. But Bob, looking at only his particle, just sees a random result. He can't tell whether his particle is randomly spin down or entangled spin down. The results look identical. Only when Alice and Bob later compare the results using conventional, slower-than-light communication do they discover the correlation. There's no way for Alice to manipulate her measurement to send a message to Bob. She can't control what result she gets. It's genuinely random from her perspective. She can choose what property to measure, spin on this axis versus that axis. But Bob's results still appear random to him, regardless of Alice's choice. The correlations are only apparent when you bring the two datasets together using conventional communication. This reveals something profound. The speed of light limits causal information, the kind of information you can use to send messages or exert influence. But quantum entanglement involves what we might call correlation information, a more subtle kind of information that doesn't allow signaling, but does create non-local correlations in the universe. Think of it like this. Before either measurement, the total system has a certain amount of information about the joint state. When Alice measures her particle, she doesn't create information ex nihilo or send information to Bob's particle. Rather, she's revealing pre-existing correlation information that was stored in the joint quantum state. The spookiness isn't particles sending signals. It's that quantum correlation information doesn't live in either particle separately. It lives in the joint state, independent of distance. This distinction between causal information that respects the light speed limit and correlation, information that's non-local, is one of the deepest insights quantum mechanics gives us about reality. It tells us that the universe has a richer information structure than classical physics imagined. But there's an even stranger implication lurking here. If entanglement creates these perfect correlations across arbitrary distances, and if these correlations are truly fundamental, rather than the result of hidden variables, then in some sense, the two particles aren't really separate. Despite being separated by space, they remain part of a single quantum system. Distance in space doesn't translate to separation in the quantum information structure of the universe. This leads to what physicist Leonard Susskind calls EREPRA, proposed connection between quantum entanglement and wormholes in spacetime. Einstein and Rosen proposed that black holes might be connected by bridges in spacetime called Einstein-Rosen bridges or wormholes. Susskind suggests that quantum entanglement, EPR, and wormholes, A, might be two descriptions of the same phenomenon. Entangled particles might be connected by tiny quantum wormholes. If true, this would mean that spacetime itself, the arena where the speed of light is defined, emerges from quantum entanglement. Space and distance would be consequences of the pattern of quantum entanglement between underlying quantum bits of information. And the speed of light would reflect something about how information is encoded in this quantum structure. This is getting at something profound. Maybe we've been thinking about this backward. We've been asking, how does the universe enforce the speed of light limit? But maybe the better question is, what is spacetime really? If spacetime emerges from quantum information, and the speed of light is a property of spacetime's geometry, then the speed of light is telling us about the information theoretic structure of reality. In 1995, physicist Ted Jacobson showed that Einstein's field equations, the fundamental equations describing how spacetime curves in response to matter and energy, can be derived from thermodynamics and the assumption that information is locally conserved. Spacetime geometry isn't fundamental. It's an emergent description of something deeper, having to do with information and entropy. The speed of light, in this view, is the speed at which thermodynamic equilibrium propagates. It's the rate at which information can spread through the network of quantum correlations that underlies reality. When you change something here, the change propagates through the network of causal connections at speed c, updating the information state of increasingly distant parts of reality. This connects to work by physicists like Eric Verleen, who proposed that gravity itself is an emergent entropic force arising from information theory. In this picture, familiar concepts like space, time, mass, and force are all emergent properties of a deeper information theoretic substrate. And constants like the speed of light aren't arbitrary parameters. They reflect the information geometry of this substrate. Here's what will blow your mind. If this is right, then asking, why is the speed of light 299,792,458 meters per second? Is like asking, why is the data rate of the universe what it is? The speed of light is the universe's processing speed, the tick rate of reality. It's the speed at which the quantum state of the universe updates itself. Some physicists take this even further. They suggest that the universe is fundamentally a quantum computer, and physical law is the algorithm it's running. The speed of light would then be related to the computational complexity of updating the quantum state, how much computation is required per unit volume per unit time. Space would be emergent from how information is encoded, and the speed of light would be the speed at which computational updates propagate through this information structure. This sounds like science fiction, but it's grounded in real mathematics and physics. It's an active area of research connecting quantum information theory, quantum gravity, string theory, and holography. And it suggests something startling. The reason nothing can go faster than light is the same reason your computer can't compute faster than its clock speed allows. The universe has a finite processing rate, and light speed is that rate. But we haven't answered the deepest question yet. Why this specific rate? Why this particular number? Is it arbitrary, or is there some deeper principle that determines it? To answer that, we need to look at the fine structure constant and the relationships between fundamental constants. And what we'll find is that the speed of light is part of a web of constants that all conspire together to make a universe where observers like us can exist. Change any of them, and reality breaks. Let's talk about something called the fine structure constant, because it's going to reveal just how interconnected the speed of light is with everything else in the universe. The fine structure constant, denoted alpha. Alpha is a dimensionless number approximately 1/137th. It has no units. It's the same value whether you measure it in meters, light years, or nanometers, whether you're using seconds, years, or Planck times. This makes it truly fundamental. It's a pure number built into the fabric of reality. The fine structure constant describes the strength of the electromagnetic interaction between elementary charged particles. It's defined as alpha equals E squared, 4c, where E is the electron charge, epsilon ebb is the permittivity of free space, k is the reduced Planck constant, and c is the speed of light. Notice that c appears in the denominator. The speed of light is literally built into the fundamental constant that determines how strongly charged particles interact. Here's where it gets interesting. If you change the speed of light, you change the fine structure constant, unless you simultaneously adjust other constants to compensate. And if you change the fine structure constant, you change chemistry. The fine structure constant determines the energy levels of electrons in atoms, the strength of chemical bonds, the stability of molecules. Change it by more than a few percent, and atoms wouldn't form molecules. Chemistry wouldn't work. Life couldn't exist. Physicist Freeman Dyson once said that the fine structure constant is the number physicists would most like to understand, because it seems to hold the key to the structure of the universe. Why 1/137th, and not 1/100th or 1/200th? Nobody knows. But we know it can't be too different from its actual value, or we wouldn't be here to ask the question. This is connected to what's called the anthropic principle, the idea that we should expect to observe a universe compatible with our existence. We can't observe universes where the constants are so different that conscious observers can't evolve. This doesn't explain why the constants have the values they do in an ultimate sense, but it constrains what values we should expect to measure. Some physicists take this further with the multiverse hypothesis. If there are countless universes with different values of fundamental constants, only those universes where the constants fall within the narrow range that permits complexity and life will have observers. We find ourselves in a universe with the right speed of light, not because there's anything special about this universe, but because universes with very different speeds of light don't have anyone wondering about it. This is controversial. Many physicists dislike anthropic reasoning because it seems to give up on finding a deeper explanation. If every possible value exists somewhere in the multiverse, then asking why this value becomes why am I in this particular universe, which is less satisfying than finding a unique mathematical principle that determines the value. But here's the thing, even if the multiverse exists, the fine structure constant and the speed of light still have to be related to each other and to other constants in specific ways within each universe. The structure of physics, the equations themselves, constrain what combinations are possible. You can't just dial up the speed of light arbitrarily. Other constants would have to adjust to maintain consistency. For instance, the speed of light is related to the Planck length and Planck time, the smallest meaningful scales of distance and time in quantum gravity. The Planck length is approximately 1.6 times 10 meters, and the Planck time is approximately 5.4 times 10 seconds. These scales are defined by combining fundamental constants, the gravitational constant g, the Planck constant k, and the speed of light c. They represent the scale at which quantum effects and gravitational effects become equally important, where quantum gravity becomes essential. The Planck scales are thought to represent the fundamental graininess of spacetime itself. Below these scales, our current theories break down. Space and time might not be continuous, but discrete, made of tiny quanta. And the relationships between Planck scales all involve the speed of light. What this suggests is that the speed of light isn't just a random parameter. It's part of the dimensional structure of reality. It connects the quantum realm, represented by K, with the gravitational realm, represented by G, and with space-time geometry, represented by C. These constants form a mathematical structure that defines what we mean by space, time, mass, and energy. Physicist Max Tegmark proposed that the universe is fundamentally mathematical, that physical reality is a mathematical structure. In this view, asking why the speed of light has its value is like asking why pi equals 3.14159, because that's what pi is in the mathematical structure that describes circles. The speed of light would simply be a parameter in the mathematical structure that is our universe. But even within Tegmark's mathematical universe hypothesis, there's still the question: what selects which mathematical structure? Are all mathematical structures realized as physical universes somewhere? Or is there some deeper principle, perhaps related to logical consistency or computational simplicity, that selects our particular structure? One intriguing idea comes from loop quantum gravity and causal set theory approaches to quantum gravity that suggests spacetime is fundamentally discrete, made of tiny elementary units. In these theories, the speed of light emerges from how these discrete spacetime atoms are connected. It would be analogous to the speed of sound in a crystal, emerging from the spacing and stiffness of atoms in the crystal lattice. The speed of light would reflect the stiffness and spacing of spacetime atoms. If this is right, then the speed of light is determined by the Planck scale structure of spacetime. Change the properties of spacetime atoms, and you change the speed of light. But those properties themselves would need to be consistent with the existence of quantum fields, particles, and forces. Everything constrains everything else in a web of logical necessity. This brings us to a profound realization. The universe doesn't know the speed of light in the sense of checking some cosmic parameter and enforcing it. Rather, the speed of light is an inevitable consequence of the logical and mathematical structure of reality. It's built into what it means for there to be spacetime, quantum fields, and causal structure. Think of it this way. A circle doesn't know its circumference should be pi times its diameter. The relationship is definitional. It's what makes it a circle in Euclidean geometry. Similarly, a universe with quantum fields, relativity, and gravity doesn't know the speed of light should be 299,792,458 meters per second. That value emerges from the geometric and algebraic structure of the theories, describing how fields in spacetime interact. But here's the part that should make you uncomfortable. We still don't have a complete theory of quantum gravity. We don't fully understand how quantum mechanics and general relativity fit together at the Planck scale. String theory, loop quantum gravity, and other approaches all have different pictures of what's fundamental. Until we have a complete theory, we can't definitively answer why the speed of light has the value it does. What we can say is this: the speed of light is deeply interconnected with every other fundamental constant and every other feature of physics. It's not a free parameter that could be adjusted independently. It's part of a tightly integrated web where changing one piece would cascade through everything else, likely breaking the universe's ability to support structure, complexity, and ultimately life. And that brings us to perhaps the most unsettling possibility. Maybe there is no deeper why. Maybe the speed of light, along with the other fundamental constants, just is. Maybe at the bottom of reality, there are brute facts aspects of existence that don't have further explanation, because they're the foundation on which all explanations rest. This doesn't mean we stop investigating, but it means we might need to adjust our expectations about what kind of answer is even possible. The physicist John Wheeler, who coined the term black hole and mentored many important physicists, spent his later years obsessing over what he called the participatory universe. He believed that observers conscious, beings asking questions and making measurements, were somehow essential to bringing reality into existence. He asked why the universe has the laws and constants it does, and wondered whether quantum mechanics, with its dependence on measurement, held the key. Wheeler's ideas remain controversial and somewhat mystical, but they point to something worth considering. Maybe the question, how does the universe know the speed of light, is actually backwards. Maybe the universe doesn't know anything. Maybe the speed of light is simply part of the boundary conditions of existence, and any universe that permits observers to evolve will have whatever speed of light is consistent with that possibility. This might sound like we're giving up, but actually it's pointing toward a different kind of answer, one grounded in the logical structure of possible universes, rather than in mechanisms within our universe. The speed of light would be explained not by some process that enforces it, but by the constraints of mathematical consistency and the requirements for a universe to be observer permitting. Let me give you something concrete to hold on to as we go even deeper. Right now, you're sitting still, or so you think, but you're actually moving through space-time at the speed of light. All your motion is through the time dimension because you're not moving significantly through space relative to Earth. A photon is also moving through space-time at the speed of light, but all its motion is through space with none through time. The speed of light isn't really a speed limit on motion. It's a description of how all things, without exception, move through space-time. Mass just determines how that motion is distributed between spatial and temporal dimensions. This reframing makes the constancy of light speed less mysterious. It's not that the universe enforces some speed limit. It's that everything is always moving through four-dimensional spacetime at the same fundamental rate. The apparent differences in speed are really differences in direction through spacetime. Light goes purely spatial. You go mostly temporal. And the speed of light is the conversion factor that relates these directions. It's the spacetime Pythagorean theorem. In the next section, we're going to explore what happens at the boundary, what happens when you try to reach light speed, why it's impossible for anything with mass, and what this reveals about the nature of mass itself. Because mass isn't some intrinsic property objects have. Mass is resistance to acceleration, and that resistance is intimately connected to the Higgs field and to how objects interact with spacetime. Understanding mass will show us why the speed of light is truly a universal limit, and what that limit is really protecting. Here's a question that seems simple, but opens up a rabbit hole. Why can't anything with mass reach light speed? The usual answer is, it would take infinite energy. But that just raises another question. Why would it take infinite energy? What is it about the universe that makes acceleration harder and harder as you approach light speed? Let's start with Einstein's most famous equation. E equals mc. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are equivalent. They're different forms of the same thing. But there's a more complete version of this equation that Einstein actually used. E squared equals mc squared squared plus pc squared, where p is momentum. This equation relates the total energy of an object to both its rest mass and its momentum. When an object is at rest, p equals 0, this reduces to E equals mc. But when the object is moving, it has additional energy from its motion kinetic energy. Here's where it gets interesting. As an object's velocity approaches light speed, its momentum doesn't increase linearly like in Newtonian physics. Instead, momentum increases toward infinity according to the formula PGmV, where gamma is the Lorentz factor. 1 square root 1 v squared per c squared. Look at what happens to gamma as v approaches c. When v equals 0, gamma equals 1. When v equals 0.5 c, gamma approximately equals 1.15. When v equals 0.9 c, gamma approximately equals 2.29. When v equals 0.99 c, gamma approximately equals 7.09. When v equals 0.999 c, gamma approximately equals 22.4. As v gets arbitrarily close to c, gamma approaches infinity. This means the momentum, and therefore the energy required to reach that velocity, also approaches infinity. But why? Why does nature have this particular mathematical structure where the Lorentz factor blows up at light speed? Here's the deep answer. It's because spacetime has a hyperbolic geometry, not a Euclidean one. In Euclidean geometry, distances are calculated with the familiar Pythagorean theorem. Distance squared equals x squared plus y squared plus z squared. In spacetime, we calculate the spacetime interval using a modified version. Interval squared equals ct squared xy squared z. Notice the minus signs. This hyperbolic structure is what makes spacetime fundamentally different from space alone. When you try to accelerate to light speed, you're trying to rotate your 4-velocity vector in this hyperbolic spacetime geometry. Your 4-velocity always has the same magnitude, c, but its direction determines how fast you're moving through space versus time. As you accelerate, you're rotating from pointing mostly in the time direction toward pointing more in spatial directions. Here's the crucial bit. In hyperbolic geometry, there's an asymptotic boundary you can approach but never reach. That boundary is the light cone, the set of directions in spacetime corresponding to light speed. Objects with mass have 4 velocities inside the light cone. Light and other massless particles have 4 velocities exactly on the light cone. And nothing can have a 4 velocity outside the light cone, because that would correspond to moving backward in time. From some reference frames, causality would break. The infinite energy required to reach light speed is a consequence of this geometric structure. You're not fighting against some force. You're trying to rotate your 4-velocity to an asymptotic boundary of the geometry. It's geometrically impossible, which manifests physically as requiring infinite energy. But this raises a question. Why do photons effortlessly sit right on this boundary while we require infinite energy to get there? The answer has to do with mass. Specifically, photons have 0 rest mass while we have positive rest mass. But what is mass, really? In the 1960s and 70s, physicists Peter Higgs, Francois Englert, Robert Brout, and others developed a theory of how particles acquire mass. The mechanism involves a quantum field that permeates all of space, the Higgs field. Particles that interact with the Higgs field acquire mass proportional to the strength of that interaction. Particles that don't interact with the Higgs field, like photons, remain massless. Think of it like this. Imagine space is filled with a thick syrup, the Higgs field. Some particles interact strongly with the syrup, experiencing lots of resistance as they try to move. These are particles with large mass, like the top quark. Some particles interact weakly with the syrup, experiencing less resistance. These are particles with small mass like electrons. And some particles don't interact with the syrup at all, gliding through it effortlessly. These are massless particles like photons. But here's what's wild. The syrup isn't in space. It is space, or at least, it's an integral part of the quantum vacuum. The Higgs field has a non-zero value everywhere in the universe, even in the emptiest vacuum. This vacuum expectation value of the Higgs field is what gives particles their mass. In 2012, the Large Hadron Collider at CERN discovered the Higgs boson, the particle that's a quantum excitation of the Higgs field, confirming this theory. This was huge because it explained where mass comes from. But it also revealed something profound about the speed of light. The speed of light is what particles move at when they don't interact with the Higgs field. Light speed isn't a maximum that particles approach. It's the natural, default speed of motion through spacetime. Mass is what slows particles down from light speed. Let me say that again, because it's crucial. Everything is trying to move at light speed. That's the natural state. Mass is a form of resistance that prevents particles from reaching that speed. The more mass, the more resistance, the harder it is to accelerate toward light speed. This flips our usual intuition. We think of light speed as this incredibly fast speed that only special massless particles can reach. But actually, light speed is the speed of spacetime itself. It's the speed at which changes propagate, at which causality operates, at which the universe updates. Massless particles simply don't have anything slowing them down from this natural speed. Now here's where it gets even stranger. Mass isn't just resistance to acceleration in space. It's also resistance to acceleration through time. When you're sitting still in space, you're moving through time at the maximum rate from your own reference frame. When you start moving through space, you start moving more slowly through time. Your mass determines how your space-time velocity is distributed between time and space. This connects to something called the equivalence principle, one of Einstein's key insights leading to general relativity. The equivalence principle states that gravitational mass, the charge that responds to gravity, is exactly equal to inertial mass, the resistance to acceleration. This seemed like a strange coincidence until Einstein realized it was revealing something fundamental. Gravity isn't a force in the traditional sense. It's the curvature of space-time itself. When you're standing on Earth's surface, you're not being pulled down by a force. You're trying to move along your natural path through space-time, a geodesic, but Earth's surface is in the way, constantly accelerating you upward. It feels like you're being pulled down, but actually the ground is pushing you up, preventing you from following your natural free-fall trajectory. This is mind-bending, so let me give you an analogy. Imagine you're on a spinning merry-go-round and someone throws you a ball. From your rotating perspective, the ball seems to curve. You might think there's a force deflecting it, but from an outside perspective, the ball is moving in a straight line. You're the one rotating. Gravity is similar. Objects in freefall, like the International Space Station orbiting Earth, are moving in straight lines through curved spacetime. We see their paths as curved because we're not in freefall. We're standing on a surface that's accelerating us away from our natural geodesic. The speed of light plays a crucial role in all of this because it's the conversion factor in the spacetime metric. When mass curves spacetime, it's actually changing how we measure distances and times in that region. And those changes affect light and massive particles differently. Light always travels at the same speed locally, but the path it takes through curved spacetime can bend, and its wavelength can shift. This is why black holes are black. At the event horizon of a black hole, spacetime is curved so extremely that light cones tip over. Inside the event horizon, all future directed paths, even for light, lead toward the singularity. You can't escape because there's no direction in spacetime that leads outward. The future is literally inward. The speed of light sets the boundary of the black hole, the distance from the singularity where light can just barely escape. The radius of this boundary, the Schwarzschild radius, is directly proportional to the mass of the black hole and inversely proportional to the square of the speed of light. R equals 2 gm per c squared. The speed of light determines how much mass it takes to create a black hole of a given size. Change the speed of light, and you change the structure of black holes, which would cascade through astrophysics, affecting star formation, galaxy structure, and the evolution of the universe. Physicist Kip Thorne, who won the Nobel Prize in 2017 for his work on gravitational waves, has studied black holes extensively. He's shown that the extreme spacetime curvature near black holes creates effects, like gravitational time dilation, so severe that if you watched a clock falling into a black hole, you'd see it slow down and essentially freeze as it approached the event horizon. The clock experiences time normally from its own perspective, but the warping of spacetime makes its proper time diverge from coordinate time outside. This time dilation is again governed by the speed of light specifically, by how light cones tilt in curved spacetime. The geometry of spacetime, the nature of gravity, the structure of black holes, the behavior of time, all of it connects back to this one conversion factor between space and time that we call the speed of light. Here's what should blow your mind. The speed of light isn't fast. I know that sounds crazy. It's 299,792,458 meters per second. But think about it differently. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star takes over 4 years. Light from the Andromeda galaxy takes 2.5 million years. The observable universe is 93 billion light years across, meaning light hasn't had time to traverse it even once since the Big Bang 13.8 billion years ago. If light speed were infinite, if changes could propagate instantaneously, the universe would be radically different. Causality would work differently. There'd be no limit on how quickly systems could interact or exchange information. A finite speed of light creates a kind of cosmic isolation, ensuring that distant regions of the universe are effectively separate, unable to influence each other or even know about each other's current state. This finite speed has profound implications for cosmology. There's a cosmic horizon, a distance beyond which we cannot see, because light from those regions hasn't had time to reach us yet. There are parts of the universe we will never be able to observe, no matter how long we wait or how powerful our telescopes become, because the expansion of the universe is carrying those regions away from us faster than light can traverse the intervening space. Wait faster than light? Yes, space itself can expand faster than light speed, because space isn't a thing moving through spacetime. It is spacetime. The speed of light limit applies to objects moving through space, not to space itself changing. This is how the universe can be larger than 13.8 billion light years across, even though it's only 13.8 billion years old. Space has been expanding, stretching the distances between galaxies, and that expansion doesn't violate relativity. But this raises a fascinating puzzle. If distant regions of the universe are beyond each other's cosmic horizons and have never been in causal contact, why do they look the same? Why do they have the same temperature, the same density, the same laws of physics? This is called the horizon problem, and it's one of the motivations for cosmic inflation, the theory that the very early universe underwent a period of exponential expansion much faster than light speed. During inflation, regions that are now separated beyond their horizons were once close enough to interact and equilibrate. Then, inflation stretched them apart to vast distances. This solves the horizon problem, but creates new questions. What drove inflation? What stopped it? And why did it leave the universe with the precise flatness and uniformity we observe? The answers to these questions involve the speed of light because inflation's dynamics depend on how quickly fields can change and how causal influence propagates. The entire structure of cosmic history, from the Big Bang through inflation to today, is governed by the interplay between quantum fields, gravity, and the speed of light causality limit. We're starting to see that the speed of light isn't just some random parameter. It's woven into every aspect of how the universe works, from the quantum scale to the cosmic scale. It determines the structure of spacetime, the behavior of matter and energy, the evolution of the cosmos. Change it even slightly, and the universe becomes unrecognizable, probably unable to support the complexity needed for life and consciousness. But we still haven't addressed the most personal question. What does all this mean for you? How does the speed of light affect your daily life, your consciousness, your place in the cosmos? That's what we're exploring next, and the answer is far more profound and intimate than you might expect. Let's bring this home. Let's talk about what the speed of light means for your life, your perception, your very existence. Because the speed of light isn't just some abstract physics constant. It's literally limiting and shaping every moment of your conscious experience right now. First, let's talk about perception. You think you see the world in real time, but you don't. Everything you see is the past. The light reflecting off this screen or this page traveled to your eyes, taking a tiny but non-zero amount of time. If you're reading on a phone a foot away, the light took about a nanosecond. If you look across the room at something 10 feet away, the light took about 10 nanoseconds. Look at the moon? That's 1.3 seconds ago. The sun? 8 minutes ago. The stars? Years, decades, millennia ago. You never see anything as it is now. You only see the past. The speed of light creates a fundamental delay between reality and your perception of it. Now, for everyday objects, this delay is so small you'd never notice. But conceptually, it means the present moment you're experiencing isn't the actual present. It's a reconstructed past assembled by your brain from light that took time to arrive. But here's where it gets really interesting. Your consciousness doesn't happen instantly either. Neural signals in your brain travel at speeds between 1 and 120 meters per second, depending on the type of neuron. Much, much slower than light speed. Your visual processing alone takes about 100 to 150 milliseconds from when light hits your retina to when you consciously perceive the image. That's 100 million times longer than the time light took to travel from the object to your eye. So there's this cascade of delays: light travel time, neural processing time, and the mysterious gap between neural activity and conscious experience. You exist perpetually in the past, experiencing a mental simulation your brain constructs from delayed information. The now you experience is a cognitive construct, not physical reality. This has philosophical implications. If you and I are looking at each other, I'm seeing where you were a few nanoseconds ago, and you're seeing where I was a few nanoseconds ago. We're never actually seeing each other in the same now. And if we're moving relative to each other, the situation gets even weirder. Relativity of simultaneity means that events I consider simultaneous are not the same events you consider simultaneous. We literally disagree about what now means across any spatial separation. The present moment, the thing we all intuitively believe we share, doesn't exist as an objective feature of reality. It's relative, observer-dependent, and ultimately a useful fiction our brains create to help us navigate the world. The speed of light is the parameter that makes this relativity of simultaneity significant. If light speed were infinite, there'd be a universal now. But it's finite, so reality has this strange structure where space-time is sliced differently by different observers. Now let's think about causality. Every decision you make, every action you take, propagates outward from you at the speed of light or slower. When you send a text message, electromagnetic waves carry it at light speed. When you speak, sound waves carry your words at the speed of sound, much slower than light. When you physically touch something, the interaction is mediated by electromagnetic forces between atoms, and those forces propagate at light speed. This means your causal influence has a boundary that expands at light speed. Everything you've ever done has affected the universe within a growing sphere, expanding at light speed from the space-time locations where you did those things. Nothing you've done can have affected anything outside your past light cone, and nothing outside your past light cone can have affected you. Think about what this means. When you were born, your causal past light cone was limited to things that could have influenced your birth. As you age, your past light cone expands, encompassing more of the universe. At each moment, the region of space-time that can causally interact with you grows. You're connected to an ever-expanding portion of the cosmos. But here's the poignant part. You will never be connected to the entire universe. There are regions of space that are receding from us so fast due to cosmic expansion that their light will never reach us. No matter how long we wait, we can never observe them, never affect them, never be affected by them. They exist in a region of spacetime that is permanently disconnected from us. The speed of light, combined with cosmic expansion, creates a fundamental cosmic loneliness. This has implications for life elsewhere in the universe. If there's intelligent life in distant galaxies, we may never know. They may never know about us. Even if both civilizations persist for millions of years, if they're beyond each other's cosmic horizons, they remain forever isolated. The speed of light doesn't just limit how fast we can travel. It limits who we can ever meet, what we can ever know, what parts of reality are even accessible to us in principle. Some people find this depressing. I find it strangely beautiful. The speed of light creates intimacy through isolation. The region of spacetime you can interact with your cosmic neighborhood is limited, making your interactions with it more precious. Every person you meet, every star you observe, every photon that reaches your eye is part of your cosmologically rare causal neighborhood. You're not just physically close to the people in your life, you're causally, cosmologically connected to them in a way you'll never be connected to most of the universe. This leads to something profound: locality in relationship. Because causal influence can only propagate at light speed, the universe has a local structure. What happens here affects what's nearby, which affects what's next to that, creating a causal web. You can't have instantaneous action at a distance, except in the subtle quantum sense we discussed earlier, which doesn't allow actual signaling. This locality is what allows for structure, persistence, and meaningful relationships. If the speed of light were infinite, everything would interact with everything instantaneously. There'd be no notion of here versus there, no separation between causes and effects, no time for things to unfold. The universe would be a single instantaneous now moment. There'd be no narrative, no sequence, no becoming. The finite speed of light creates the possibility of stories, including your story. Your life is a timeline, in space-time a world line. It starts at your birth and extends through space-time to where you are now, and it will continue until your death. Your entire life, from a space-time perspective, exists as a complete path through four-dimensional reality. The you reading this sentence is a cross-section of that world line at a particular moment. Past you and future, you are other cross-sections of the same world line. The speed of light determines the structure of your world line. It determines what paths through space-time are possible for you. You can't suddenly jump discontinuously to a different location. You have to travel continuously through space, and you can't go faster than light. Your world line must always stay inside the light cone. This constraint shapes the space of possible futures available to you at each moment. But here's something wonderful. While you're constrained by the light cone, you have freedom within it. At each moment, there's a range of possible futures, all the paths your world line could take that don't exceed light speed. Your choices, your actions, your responses to circumstances, these navigate between possible futures, selecting which path your world line actually takes. The speed of light doesn't eliminate free will, whatever that means. It defines the boundary of possible experiences. Now let's talk about something even more intimate: your body. You are matter and energy arranged in a specific pattern. The matter in your body, the atoms, the molecules, these aren't moving through space-time at light speed because they have mass. But the forces holding you together, the electromagnetic forces between atoms and molecules, the electrical signals in your neurons, these propagate at light speed. Your body is held together by electromagnetic interactions. When you tense a muscle, electromagnetic forces are coordinating between billions of molecules. These coordinations can't propagate faster than light. For an object the size of a human body, roughly 2 meters, light takes about 6.7 nanoseconds to traverse. This sets a fundamental limit on how fast signals can coordinate across your body. Now, 6.7 nanoseconds is incredibly short. Biological processes operate on much slower timescales. Your neurons fire at rates of milliseconds, not nanoseconds. But conceptually, The speed of light sets an absolute limit on how tightly integrated a physical system can be. For very large objects or very fast processes, light speed delays become significant. This has implications for thought and consciousness. Some philosophers and scientists have speculated about whether consciousness could be a quantum phenomenon requiring coordinated quantum states across large portions of the brain. If so, the speed of light would limit how quickly quantum information could spread, constraining what kinds of conscious experiences are physically possible. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that consciousness involves quantum computations in cellular structures called microtubules. This controversial theory aside, any physical theory of consciousness must respect the speed of light constraint on information propagation. Your thoughts, whatever their physical basis, unfold at rates limited by how fast signals can move through the neural substrate. Here's a weird thought from a photon's perspective. Its entire journey, even across billions of light years, happens in zero time. The photon doesn't experience duration. It's created and absorbed in the same moment of its proper time. Now, you're not a photon. You have mass, so you experience time. But what this reveals is that the experience of duration, of time passing, of before and after, this is tied to having mass, to moving through spacetime at less than light speed. If you could somehow reach light speed, you can't, but hypothetically, time would stop for you. From your perspective, you'd instantly reach any destination, no matter how far. But from an outside perspective, you'd take a finite time to get there. This divergence between proper time, your experienced time, and coordinate time measured by outside observers, is the heart of time dilation. What this means is that the passage of time, your aging, your memories accumulating, your experience of cause and effect, all of this is a consequence of not moving at light speed. Your mass, by preventing you from reaching light speed, grants you the gift of experiencing duration, of having a story that unfolds sequentially. Light doesn't have this. Light exists in an eternal now. This connects to something profound about memory and identity. You are a pattern that persists through time, accumulating changes. Your identity depends on continuity. The you of yesterday is connected to the you of today through continuous existence and causal processes. If you could teleport instantaneously from here to Mars, would the person arriving be you? Philosophers debate this, but physics places constraints. If information about you is transmitted to Mars and a copy is reconstructed, that transmission can't exceed light speed. The teleportation would take at least several minutes, and during that time, there'd be no continuous you-just information encoding your pattern. The speed of light limits the space of possible technologies, possible experiences, possible modes of existence. You can't have instantaneous travel or communication across astronomical distances. You can't upload your consciousness to a computer and instantly transfer it to a new body on a distant planet. Any process that moves you or information about you is bound by light speed causality. This might seem like a limitation, but it's also what makes you coherent. If different parts of you could influence each other instantly across arbitrary distances, there'd be no local integrity to your existence. You'd be smeared across spacetime in a way that makes identity unclear. The light speed limit enforces locality, and locality is what allows for bounded, coherent entities like you. Let me share something that shifted my perspective. The speed of light is the speed of now. It's the rate at which the present moment propagates from causes to effects. Every moment, the state of the universe is updating, with changes spreading at light speed. You exist at the leading edge of this propagation, experiencing one moment after another as the cosmic computation unfolds. Your consciousness isn't separate from this process. It is this process, or at least a localized eddy in it. Your awareness of reading these words is part of the universe's causal structure updating itself. The speed of light is the clock speed of reality, and your conscious experience is a subroutine running at that clock speed, or slower, even neural delays. This means you're not observing the universe from outside. You're a process within the universe observing itself. And the speed of light determines the rate at which you can receive new information, process it, and respond. It sets the tempo of your existence. Some physicists and philosophers take this further, suggesting that consciousness itself might be related to information integration, the way the system combines information from different sources. The speed of light would then limit how quickly consciousness can integrate information from spatially separated sensors, like your two eyes, your ears, your skin. Your unified conscious experience emerges from a process that respects light speed causality. This isn't some distant abstraction. Right now, as you read this, photons are arriving at your retina, triggering chemical reactions that send electrical signals through your optic nerve, which activate neural patterns that somehow mysteriously give rise to your conscious experience of seeing these words. Every step in that process respects the speed of light. You are a localized process in spacetime, unfolding at rates determined by fundamental constants like c. And here's the part that fills me with awe. You are made of matter that was forged in the cores of stars billions of years ago. Those stars exploded, scattering matter across space. That matter aggregated into new stars and planets. Eventually, on at least one planet, the matter organized into replicating patterns we call life. Over billions of years, natural selection shaped those patterns into increasingly complex forms, culminating in brains capable of wondering about their own origins. Every step of that process, stellar nucleosynthesis, supernova, planetary formation, the origin of life, evolution, the development of consciousness, every step was governed by the same laws of physics, the same fundamental constants, including the speed of light. You are the universe's way of looking back at itself, and that self-observation is only possible because the universe has this particular structure, with this particular speed of causality. The speed of light isn't just a fact about the universe. It's a fact about you. It shapes what you can experience, what you can know, what you can become. It creates the stage on which your life unfolds and sets the tempo of that unfolding. You are not separate from the cosmic speed limit. You are an expression of it. Now we need to confront something that might challenge everything we've discussed. What if the speed of light isn't actually constant? What if it varies depending on the conditions, the scale, or the era of the universe? This might sound like fringe science, but there are legitimate physicists exploring these ideas, and their work reveals even deeper truths about what the speed of light really represents. In the standard model of cosmology and particle physics, the speed of light is assumed to be a fundamental constant that has the same value everywhere and at all times. But there are reasons to question this assumption, or at least ask what we really mean when we say a constant is constant. First, there's the horizon problem I mentioned earlier. The cosmic microwave background, the afterglow of the Big Bang, has almost exactly the same temperature in all directions, to within about 1 part in 100,000. But regions of the sky, separated by more than about 2 degrees, have never been in causal contact under standard Big Bang cosmology. They're beyond each other's light horizons. So how did they end up at the same temperature? The standard solution is cosmic inflation, a period in the universe's first fraction of a second when space expanded exponentially fast, faster than light speed, which is allowed because it's space itself expanding, not things moving through space. But here's an alternative. What if the speed of light was much faster in the very early universe? If light speed were higher then, distant regions could have been in causal contact even without inflation. In 1999, João Magueio and Andreas Albrecht independently proposed varying speed of light, VSL, theories as an alternative to inflation. In these theories, the speed of light was much higher in the extremely hot, dense conditions of the early universe and has been decreasing ever since. This could solve the horizon problem without requiring inflation? There's a major problem with this idea, though. If you change the speed of light, you have to carefully adjust other constants to avoid breaking physics. Remember that the speed of light appears in Maxwell's equations, in the definition of the fine structure constant, in the relationship between mass and energy. Change c, and you have to decide what happens to these other relationships. Maggeo's approach involves modifying the theory in a way that preserves certain dimensionless ratios, like the fine structure constant, while allowing c to vary. This requires that other dimensional constants vary in coordinated ways. It's mathematically possible, but it raises the question: if multiple constants are varying together to preserve certain ratios, are the ratios the more fundamental things? Is the speed of light even a meaningful concept separately from these ratios? This connects to a deeper issue. When we measure the speed of light, we're using rulers to measure distance and clocks to measure time. But rulers and clocks are made of atoms, and atom sizes and oscillation frequencies depend on fundamental constants. If those constants change, our measuring devices change with them. How would we even know if the speed of light had changed? Physicist Michael Duff has argued that asking whether constants like the speed of light change is actually meaningless unless you specify what remains fixed as a reference. He points out that dimensional constants like c, which has units of meters per second, can only be measured relative to other dimensional quantities. What's really meaningful are dimensionless ratios like the fine structure constant. So when we ask, does the speed of light change? We're really asking, do certain dimensionless numbers that depend on c change? If those dimensionless numbers change, then in some meaningful sense, the speed of light has changed relative to other features of physics, even if we can't directly measure the change. There are ways to test this. Astronomers have looked at fine structure constant measurements from the light of distant quasars. The fine structure constant affects the spacing of spectral lines in atoms. By measuring these spectral lines from quasars billions of light years away, we're seeing what the fine structure constant was billions of years ago. Any change would show up as shifts in these spectral lines. The results are controversial. Some studies have claimed to detect tiny variations in the fine structure constant changes of perhaps 1 part per million over billions of years. Other studies find no change. The measurements are at the edge of what's technically possible, and systematic errors are hard to rule out. As of now, the scientific consensus is that if the fine structure constant varies at all, the variation is extremely small. But the mere possibility that it might vary opens up profound questions. If fundamental constants can vary with time or with physical conditions, then they're not truly fundamental. They're effective parameters that emerge from some deeper theory. This is actually expected in some approaches to quantum gravity. In string theory, for example, the values of fundamental constants, like the speed of light, depend on the geometry of extra spatial dimensions. Different geometries give different values. If the extra dimensions are dynamical, if they can change shape, then the constants would effectively vary. The landscape of string theory includes something like 10,500 possible vacuum states, each potentially giving different values for constants. This connects back to the multiverse idea. If string theory is correct, and there are many possible vacuum states, perhaps different regions of the multiverse have different values of the fundamental constants, including different effective speeds of light. We find ourselves in a region where the constants permit complex structures and observers, because, well, we couldn't exist in regions where they don't. But here's a more radical possibility that some physicists are exploring. What if the speed of light varies not with time or location, but with scale? What if quantum gravity effects at the Planck scale modify how light propagates? There's a phenomenon called quantum foam that's predicted by some approaches to quantum gravity. At the Planck scale, about 10 to 35 meters spacetime itself might be turbulent and fluctuating, with quantum uncertainties in the metric structure. Light passing through this foamy spacetime might experience tiny variations in speed, depending on the wavelength. If this is true, High-energy photons, gamma rays with very short wavelengths, might travel at slightly different speeds than low-energy photons, radio waves with long wavelengths. This effect would be incredibly tiny, maybe 1 part in 1015 or smaller, but it could accumulate over cosmic distances. Light from a gamma ray burst billions of light years away would show a measurable time delay between high-energy and low-energy photons if this effect exists. Astronomers have looked for this. When gamma ray bursts are detected, both gamma rays and lower energy light arrive. If quantum gravity creates speed variations, the different energies should arrive at different times. So far, the measurements show that if there's any energy-dependent speed variation, it's smaller than can currently be detected. This places strong constraints on quantum gravity theories. But the fact that we're even testing whether light speed depends on photon energy shows how deeply physicists are probing the nature of spacetime. The speed of light might not be a single, perfectly fixed number in all contexts. It might be an effective parameter that emerges from deeper quantum gravitational physics, and that parameter might have subtle context dependence. There's another fascinating possibility. What if the speed of light is infinite in some fundamental sense, but appears finite to us because of how we're embedded in spacetime? This sounds crazy, but it's related to ideas about holography and emergent spacetime. The holographic principle, inspired by black hole thermodynamics and developed by Gerard T. Hooft and Leonard Susskind, suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram. This implies that the three-dimensional space we experience might be emergent from two-dimensional information on a distant boundary. If space-time is emergent, if it's not fundamental, but arises from some deeper quantum information structure, then properties like the speed of light would be emergent too. They'd reflect features of how the information is organized and how it evolves, rather than being built-in parameters of a fundamental spacetime. In this picture, asking, "Why does the universe know the speed of light?" is like asking, "Why does a computer know its clock speed?" The computer doesn't know. Anything the clock speed is determined by the hardware, and all software processes are constrained by it. Similarly, the universe doesn't know the speed of light. The speed of light is a parameter of the computational substrate underlying physical reality, and all processes are constrained by it. Some physicists take this even further. What if consciousness itself is somehow connected to this information structure? What if the speed of light is related to the rate at which conscious experience updates? This is highly speculative, but physicist Donald Hoffman has proposed that spacetime itself is not fundamental. It's a user interface that conscious agents use to interact. Just like the icons on your computer desktop aren't the actual files and programs, they're representations. Spacetime might be a representational structure rather than the fundamental reality. The speed of light would then be a feature of this interface, not a feature of the underlying reality. I'm not endorsing these ideas. They're controversial and far from established science. But they illustrate that even our most fundamental concepts, like the constancy of light speed, might be more subtle than they appear. The question, how does the universe know the speed of light, might not have a simple answer, because the speed of light might not be a simple, fundamental parameter. Here's what we can say with confidence. Whether the speed of light is truly fundamental or emerges from something deeper, it's intricately connected to every other aspect of physics. Change it, and you change everything. This interconnectedness suggests that there's a deep logical structure underlying reality, a structure where the various constants and laws all fit together in a self-consistent web. This brings us to something truly profound. The universe appears to be mathematically consistent. The laws of physics, as far as we can tell, don't contradict each other. Quantum mechanics and general relativity are both internally consistent theories, even if we haven't figured out how to unite them completely. This mathematical consistency is remarkable and not obviously inevitable. Physicist Eugene Wigner wrote a famous paper titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," marveling at how mathematical structures discovered by pure thought turn out to describe physical reality with stunning precision. Why should the universe be mathematical at all? Why should equations written on paper predict the behavior of distant galaxies or tiny particles? One answer: maybe the universe is mathematics. Max Tegmark's mathematical universe hypothesis proposes that physical existence and mathematical existence are the same thing. The universe isn't described by mathematics, it is mathematics. The speed of light would then be a parameter in a mathematical structure, no more arbitrary than the number pi, and no more in need of explanation than why 2 plus 2 equals 4. This raises a vertiginous question. If the universe is mathematics, and mathematical structures exist necessarily and eternally, then does the universe exist necessarily and eternally? Is our physical reality just one possible mathematical structure among infinitely many? And if so, what determines which structure is actualized as physical existence? These questions take us to the boundary between physics and philosophy, between science and metaphysics. We're asking not just how the universe works, but why there's anything at all, and why it has the particular mathematical structure it does. Let me bring this back to Earth with something concrete. The speed of light, whether constant or variable, whether fundamental or emergent, is measurable. We can test it. We can probe its properties. We can look for variations across time, space, or energy. This is what makes these questions scientific rather than purely philosophical. We can gather evidence, make predictions, and refine our theories based on observations. The Large Hadron Collider, the Laser Interferometer Gravitational Wave Observatory, LIGO, the Event Horizon Telescope, the James Webb Space Telescope. These instruments are probing the fundamental structure of reality with unprecedented precision. LIGO detected gravitational waves in 2015, confirming Einstein's century-old prediction and demonstrating that gravitational disturbances propagate at light speed. The Event Horizon Telescope imaged the event horizon of a supermassive black hole, showing how light behaves in extreme gravitational fields. These observations constrain theories about the speed of light and spacetime structure. They show that, at least in the regimes we can currently probe, Einstein's theory holds up remarkably well. The speed of light appears constant across vast distances and extreme conditions. Gravitational waves travel at the same speed as light to within experimental precision. Black holes behave as predicted by general relativity. But there are still mysteries. Dark energy, which is causing the universe's expansion to accelerate, is poorly understood. Dark matter, which makes up most of the matter in the universe, doesn't interact with light and remains unidentified. Quantum gravity, which should describe spacetime at the Planck scale, remains elusive. Any of these might reveal new physics that changes our understanding of the speed of light. Here's what gives me hope and wonder. We don't know everything. The speed of light might have deeper explanations we haven't discovered. There might be phenomena that transcend or modify the simple constant C picture. The universe might be stranger and more beautiful than we imagine. But whether the speed of light is perfectly constant or subtly variable, whether it's fundamental or emergent, one thing is clear: it's deeply woven into the structure of reality. Understanding it requires understanding spacetime, quantum fields, gravity, thermodynamics, information theory, essentially all of fundamental physics. The speed of light isn't just one constant among many. It's a nexus connecting all the different aspects of how the universe works. And that's why the question, how does the universe know the speed of light, is so profound. It's really asking, how is the universe self-consistent? How do all the pieces fit together? Why does reality have a coherent mathematical structure rather than being chaotic and arbitrary? These are some of the deepest questions we can ask, and the speed of light is a thread that, when pulled, unravels toward the very foundations of existence. Let's explore something that will genuinely blow your mind. The speed of light might be the key to understanding why time only flows in one direction. You've probably never thought about why time has an arrow, why it causes precede effects, why you remember the past but not the future, why entropy increases, why you age. It seems obvious that time flows forward. But physically, most of the fundamental laws are time-symmetric. They work equally well running forward or backward. Newton's laws, Maxwell's equations, Einstein's field equations, even the Schrödinger equation in quantum mechanics, all of these are time reversible. If you filmed the process governed by these laws and played the video backward, you'd see something that also obeys the laws. Yet clearly, time has a direction in our experience. You can't unbreak an egg. You can't unburn fuel. You can't grow younger. This asymmetry comes from thermodynamics, specifically the second law. Entropy tends to increase in isolated systems. Entropy is a measure of disorder, or more precisely, the number of microscopic states consistent with a macroscopic description. A broken egg has higher entropy than an intact egg because there are many more ways to arrange egg molecules in a broken configuration than an intact one. But here's the puzzle. If the underlying laws are time-symmetric, why does entropy increase in one direction rather than the other? The standard answer is that the universe started in a very low entropy state. The Big Bang was highly ordered, and entropy has been increasing ever since. But this just pushes the question back. Why did the universe start with low entropy? Enter Roger Penrose. In his conformal cyclic cosmology, Penrose proposes that the universe goes through infinite cycles, with each Big Bang being both an end and a beginning. But here's the crucial bit. Entropy and the arrow of time are connected to the structure of spacetime itself, specifically to black holes and the speed of light. Black holes are entropy engines. When matter falls into a black hole, the information about that matter seems to be lost. This is the black hole information paradox, which remains controversial. The entropy of the black hole increases, encoded in its surface area. Eventually, black holes evaporate through Hawking radiation, converting mass to thermal radiation. The speed of light determines the boundary of the black hole, the event horizon. It also determines the structure of light cones, which define the causal structure of spacetime. Penrose shows that this causal structure, governed by light speed, is intimately connected to entropy and the arrow of time. Here's the key insight. The arrow of time isn't fundamental. It emerges from boundary conditions, specifically from the low entropy state of the early universe, and from how information is distributed in spacetime. And that distribution is constrained by light speed causality. Think about it this way. The speed of light determines what can influence what. It creates a causal structure, a network of possible cause and effect relationships. Entropy increase follows the causal structure. High entropy states evolve from low entropy states along causal paths. The arrow of time aligns with the direction of increasing entropy, which aligns with the causal structure defined by light cones. This means the speed of light isn't just a kinematic parameter describing how fast things move. It's a causal parameter describing the structure of cause and effect, and therefore the structure of time itself. Without the finite speed of light, there'd be no clear notion of causality, and without causality, the arrow of time becomes ambiguous. But it gets weirder. In 1949, Kirkdale, the same Dedel who proved incompleteness theorems in mathematics, discovered solutions to Einstein's field equations that describe rotating universes containing closed time-like curves. These are paths through spacetime that loop back on themselves, allowing travel to your own past. In Gigel's universe, there's no global arrow of time. You could travel in a loop and return to the same spacetime event you started from. This doesn't happen in our universe, as far as we know, but the fact that it's mathematically possible in general relativity shows that time's arrow isn't guaranteed by the laws themselves. It depends on the specific structure and boundary conditions of spacetime. The speed of light plays a crucial role in whether closed time-like curves can exist. They require specific configurations of matter and energy that curve spacetime in extreme ways. Most physically realistic configurations don't allow closed time-like curves, and the ones that do, like rotating black holes or wormholes, have features that might prevent their formation or traversal. Physicist Kip Thorne studied whether wormholes' shortcuts through spacetime could allow time travel. His conclusion: even if wormholes exist, keeping them open and traversable would require exotic matter with negative energy density. And even then, quantum effects might destroy the wormhole before you could use it for time travel. The speed of light, combined with quantum mechanics and energy conditions, seems to protect causality. There's a principle called chronology protection, proposed by Stephen Hawking, which suggests that the laws of physics prevent time travel to the past, even if the equations technically allow it. The speed of light is central to this protection. It ensures that causal influences propagate forward through time along light cones, maintaining a consistent causal order. Now here's where this connects to your conscious experience. Your sense of self, your memory, your feeling that you're moving forward through time. All of this depends on the arrow of time being consistent. If causality broke down, if effects could precede causes, your cognitive processes wouldn't make sense. Memory requires that brain states now are caused by brain states in the past, not the future. Your identity persists because there's a continuous causal chain connecting past you to present you to future you. The speed of light, by defining the causal structure, makes your existence as a temporally extended, persistent self possible. You're not just constrained by light speed spatially, you're constrained by it temporally. Your world line through spacetime must respect light speed causality, and that causality gives structure to your experience of time. Here's something that might mess with your head. From a four-dimensional spacetime perspective, your entire life past, present, and future already exists as a complete world line. This is called the block universe view. Just as all of space exists now, even though we only experience our local region, all of time exists in the eternal four-dimensional spacetime structure. In this view, the flow of time is an illusion created by consciousness. The now is just where you happen to be along your world line, like how here is where you happen to be in space. The speed of light doesn't cause time to flow. Rather, it defines the geometric structure of the block universe, determining which events are causally connected. This is philosophically disorienting. It suggests that your future already exists in some sense, that it's already out there in spacetime. Your subjective experience of moving through time is like reading a book. The whole book exists, but you experience it page by page. The speed of light defines how the pages are ordered, how events are arranged in causal sequence. But there's a counter-argument from quantum mechanics. Quantum mechanics introduces genuine randomness outcomes that aren't determined until they're measured. When a quantum measurement happens, the wave function collapses into a definite state, and which state it collapses into is fundamentally random. This suggests that the future isn't fully determined, that it's genuinely open. How do we reconcile the block universe picture with quantum indeterminacy? One approach is the growing block model. The past and present exist in the block universe, but the future doesn't exist yet. It comes into existence as quantum wave functions collapse and possibilities become actualities. The speed of light would then define the rate at which the future becomes fixed, the rate at which possibilities crystallize into definite facts. This connects to something called the quantum Zeno effect. If you continuously measure a quantum system, you can prevent it from evolving. The act of measurement collapses the wave function, and frequent measurements keep collapsing it to the same state, freezing the system. This shows that measurement observation plays a role in how quantum systems evolve through time. Some interpretations of quantum mechanics take this to mean that consciousness plays a fundamental role in reality. The physicist John von Neumann suggested that quantum wave functions collapse when they interact with a conscious observer. Most physicists reject this view as too anthropocentric, but it points to a deep mystery. How does the quantum realm of superposed possibilities become the classical realm of definite facts? The speed of light is intimately involved because it governs how quantum information propagates. When a particle's wave function collapses here, that information can't influence distant regions faster than light speed. The collapse creates a definite fact in your light cone, but regions outside your light cone remain in superposition until the information reaches them. This creates a picture where reality is constantly crystallizing from quantum possibilities into classical facts. And this crystallization propagates at light speed. You exist at the boundary between quantum and classical, experiencing the flow of time as the universe decides which of many possible futures to actualize. Here's what blows my mind about all this. The speed of light isn't just about motion through space. It's about the flow of information, the propagation of causality, the structure of time, the boundary between possible and actual. It's about the fundamental rate at which reality unfolds and determines itself. When you ask, how does the universe know the speed of light? You're really asking, how does the universe know how to be a causally structured, temporally ordered, experienceable reality? The speed of light is woven into what it means for there to be a universe at all. At least a universe that supports observers like us, who exist in time and experience causality. And here's the truly profound part. You're not separate from this process. Your consciousness exists within the causal structure defined by light speed. Your thoughts unfold at rates determined by how quickly information can propagate through your brain. Your memories are records of past causal influences. Your decisions shape future causal influences. You're a localized node in the causal web of spacetime, constrained and enabled by the same light-speed structure that governs galaxies and atoms. Let's tackle something that sounds like science fiction, but is actually serious physics. Can we break the light-speed barrier? Can we find loopholes, workarounds, or ways to effectively travel faster than light, even if we can't technically exceed light speed locally? Because if we can't, the universe is a very lonely, isolated place. And if we can, it might break causality. First, let's be clear. Special relativity definitively says that no object with mass can accelerate to or past light speed. The energy required approaches infinity as you approach c. This isn't an engineering challenge. It's a fundamental limit built into the geometry of spacetime. But there are some apparent loopholes worth exploring. First, the expansion of space. Space itself can expand faster than light, and in fact, it is. Distant galaxies are receding from us, faster than light speed, because the space between us and them is expanding. This doesn't violate relativity, because the galaxies aren't moving through space faster than light. Space itself is growing. In 1994, physicist Miguel Alcubierre proposed a theoretical faster-than-light drive based on this principle. The Alcubierre drive would create a bubble of spacetime that contracts space in front of a ship and expands space behind it. The ship itself stays stationary within its bubble, never exceeding light speed locally, but the bubble moves through space faster than light, carrying the ship with it. This is mathematically consistent with general relativity. The problem: it requires exotic matter with negative energy density to create the necessary spacetime curvature. And not just a little bit. The original design required more negative energy than the positive energy in the entire observable universe. Subsequent research has reduced the energy requirements somewhat, but it still requires exotic matter that we've never observed and might not exist. Even if it does exist, manipulating it to create an Alcubierre bubble might be impossible. And there's a causality problem. If two people with Alcubierre drives travel on certain trajectories, they could communicate with their own past, creating paradoxes. Second apparent loophole: wormholes. A wormhole is a shortcut through spacetime. connecting two distant points. If you could travel through a wormhole, you'd effectively travel faster than light without actually exceeding light speed locally. You're just taking a shorter path. Einstein and Rosen showed that black hole solutions to general relativity mathematically connect to white holes, hypothetical objects that eject matter rather than consuming it, through Einstein-Rosen bridges. But these bridges collapse too quickly for anything to traverse them. To keep a wormhole open, you'd need, you guessed it, exotic matter with negative energy. Moreover, physicist Matt Visser showed that if you could manipulate a wormhole's mouths and move them around, you could create a time machine, allowing travel to your own past. This creates the famous grandfather paradox. What if you go back and prevent your own birth? The universe would have to prevent such paradoxes, probably by preventing the creation or traversal of time machine wormholes. Third possibility, quantum entanglement. We discussed earlier that entangled particles are correlated instantly across arbitrary distances. Could we use this for faster-than-light communication? No. We've been over this, but it's worth repeating because people keep hoping for a loophole. Entanglement correlations can only be verified by comparing measurements using slower-than-light classical communication. There's no way to encode a message in the random outcomes of quantum measurements. Fourth idea, quantum tunneling. In quantum mechanics, particles have a probability of tunneling through barriers they classically couldn't cross. Some experiments have suggested that particles can tunnel through barriers in less time than it would take light to cross the same distance. Does this violate the speed limit? No. The issue is subtle and involves how you define the particle's speed during tunneling. When carefully analyzed using quantum field theory, the effective speed at which information or energy propagates never exceeds light speed. What looks like faster-than-light tunneling is actually a consequence of quantum uncertainty about when and where the particle is. Fifth possibility, tachyons. These are hypothetical particles that always travel faster than light, just as ordinary particles always travel slower than light. If tachyons exist, they'd have imaginary mass, in the mathematical sense, involving the square root of -1. They'd travel backward in time from some reference frames, creating causality issues. Most physicists think tachyons don't exist because they'd make the quantum vacuum unstable particles, and tachyons would spontaneously be created in runaway cascades. Theories that mathematically contain tachyons are usually considered pathological and need to be reformulated to eliminate them. The speed of light appears to be a genuine absolute limit, not just the asymptotic speed of ordinary particles. So it seems we're stuck. Light speed is truly the limit, and the distances between stars make interstellar travel incredibly challenging. Even traveling at a significant fraction of light speed, say 10%, would require enormous energy and would take decades to reach nearby stars. But there's a fascinating relativistic loophole: time dilation. If you could accelerate to very close to light speed, time would slow down for you relative to Earth. You could, in principle, travel across the galaxy in your own lifetime, even though thousands or millions of years pass on Earth. Imagine a spaceship that accelerates at 1 gram, Earth's gravity, providing comfortable artificial gravity continuously. After about a year of proper time for the crew, the ship would be traveling at relativistic speeds. After a few years, it would be close enough to light speed that time dilation becomes extreme. The crew could cross the galaxy in decades of their time, even though hundreds of thousands of years pass for everyone else. This is sometimes called the time dilation loophole, but it's not really a loophole. It's how relativity actually works. The catch: you can't come home to the world you left. Everyone you knew would be long dead. Civilization would have changed beyond recognition or ended entirely. You'd be time travelers to the future with no way back. This creates a profound asymmetry. You can effectively travel vast distances in your lifetime by going very fast, but you can't share that experience with anyone who stays behind. The speed of light doesn't just limit spatial separation, it limits temporal connection. High-speed travel severs you from your origins. There's another approach, generation ships. Instead of trying to make the journey in one lifetime, build enormous ships that support entire civilizations for thousands of years. The people who arrive are descendants of those who left, thousands of generations removed. This doesn't overcome the light speed limit, but it works within it. Or suspended animation. Freeze travelers for the journey and wake them at the destination. If this becomes technologically possible, it would make slow interstellar travel more practical. But it doesn't solve the fundamental problem. Travel times are still measured in years, decades, or centuries, depending on distance and speed. Here's what's fascinating. The speed of light limit doesn't just constrain travel, it constrains empires, civilizations, and communication. If humanity colonized other star systems, each colony would inevitably become independent. Communication delays of years or decades make centralized governance impossible. Each world would develop its own culture, diverging from Earth. Over thousands of years, colonies might become so different they're practically different species, and they'd never be able to fight wars in the traditional sense. By the time you learned a distant colony rebelled and sent a fleet to suppress it, centuries would pass. The rebels would have generations to prepare. The speed of light enforces a kind of cosmic federalism where distant regions must be autonomous. This has led some scientists to speculate about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing and the lack of evidence for them. One resolution: advanced civilizations don't expand much beyond their home systems because the light speed limit makes maintaining far-flung empires impractical. Each civilization stays in its local neighborhood. Or perhaps advanced civilizations transcend physical form, uploading consciousness to substrates that don't need to travel. Or perhaps they've discovered physics we don't understand that allows faster-than-light travel. We can't rule this out. Our current theories might be incomplete. But based on everything we know, the speed of light is a real fundamental limit. It's not technological, it's geometrical. It's built into the structure of spacetime itself. Breaking it would require breaking spacetime, which might not be possible or might have consequences we can't imagine. Here's a thought experiment. Imagine a civilization develops technology to create stable wormholes and uses them for faster-than-light travel. They could send messages to their own past. This creates the potential for logical paradoxes. How does the universe handle this? One possibility, the Novikov self-consistency principle, proposed by physicist Igor Novikov. It states that the universe only allows closed time-like curves that are self-consistent. Any attempt to create a paradox is thwarted by physical processes. You can't kill your grandfather because any attempt to do so will fail for mundane reasons. Your gun jams. You slip. Something prevents the paradox. This is bizarre but mathematically consistent. It means that if time travel to the past is possible, free will becomes illusory. Your choices are constrained by the requirement that history remain consistent. The speed of light, by preventing faster-than-light travel in most scenarios, might be protecting our free will by preventing closed time-like curves. Another possibility, the many-worlds interpretation of quantum mechanics. If time travel to the past is possible, it splits you off into a parallel universe. You can't change your own past, but you can visit a parallel past. This preserves consistency, but at the cost of multiplying universes. Or maybe causality violations simply cause the universe to reach an inconsistent state and break down. Maybe the laws of physics have built-in protections, chronology protection, that prevent such situations from arising. The speed of light limit is one such protection. What all this reveals is that the speed of light isn't arbitrary. It's part of a deep structure, ensuring that the universe remains causally coherent, logically consistent, and computationally tractable. Change it, allow faster-than-light travel, and you might break the consistency of reality itself. This brings us full circle to our original question. How does the universe know the speed of light? It doesn't. The speed of light is part of the axiomatic structure of reality. It's built into the rules. Asking how the universe enforces it is like asking how a chess game enforces the rule that bishops move. Diagonally, the rule defines what the game is. Reality is a structure with certain invariances, symmetries, and constraints. The speed of light is one of those constraints. It emerges from the requirement that the universe be mathematically consistent, causally ordered, and information theoretically coherent. Without it, you don't have a different universe. You have logical incoherence, paradox, breakdown. And yet, the fact that this specific value, 299,792,458 meters per second, is what maintains coherence remains mysterious. Why this number? We've explored many answers. It's connected to other constants. It emerges from Planck scale physics. It's constrained by anthropic selection. It's a parameter in a mathematical structure. But ultimately, we might be asking for a type of explanation that doesn't exist. Maybe the deepest answer is simply, this is what coherent existence requires. The speed of light is part of the answer to the question, what does it mean for there to be a universe at all? And the fact that we exist, able to ask that question, is evidence that whatever the answer is, it includes this particular value of c. We're approaching the end of this journey, and I want to address something deeply personal. What does all this mean for you? Not you as a human in general, but you specifically right now, reading or listening to these words. Because the speed of light isn't just an abstract constant in equations, it's shaping your existence in ways both profound and intimate. Every photon hitting your retina right now traveled at exactly 299,792,458 meters per second to get there. The screen you're looking at, the page you're reading, electromagnetic forces between atoms, propagating at light speed, hold it together. The neurons firing in your brain as you process these ideas, those are electrochemical, signals constrained by how fast electric fields can propagate. You exist in a light-speed universe. That's not metaphorical. The fundamental rate at which causes become effects, at which your actions propagate outward, at which new information reaches you, all of this is governed by c. You're like a character in a video game, constrained by the frame rate, except the frame rate is the speed of light and the game is reality itself. This means something important. You're always experiencing the past, not just cosmologically, like when you look at stars light years away. Right now, in this moment, the now you're experiencing is already gone. The light reaching your eyes is nanoseconds old. Your brain's processing of that light takes milliseconds. By the time you consciously experience this moment, it's already history. Your entire conscious life is lived in retrospect. You never experience the present, you only experience a running reconstruction of the recent past, assembled by your brain from delayed signals. The speed of light contributes to this delay, though neural processing contributes more. But conceptually, there's no such thing as experiencing the present moment. The present is a moving target that's always just beyond reach, perpetually becoming past before you can grasp it. And yet, this doesn't make your experience less real or less meaningful. In fact, it reveals something beautiful. Consciousness exists in the gap between physical events and awareness of them. You're not a passive observer of reality. You're an active participant, constructing a coherent experience from fragmentary, delayed information. Your brain is essentially solving an engineering problem: how to create a unified, seemingly instantaneous conscious experience from signals that arrive at different times from different sources. Light from the left side of your visual field hits your left eye at a slightly different time than light from the right side hits your right eye. Sound reaches your ears at different times, depending on where the source is. Touch signals from your toes take longer to reach your brain than touch signals from your face. Your brain synchronizes all of this, creating the illusion of a single now. It's like a conductor leading an orchestra where each musician is playing slightly out of sync, but through careful timing corrections, the conductor creates a unified performance. The speed of light and other signal propagation speeds create the temporal offsets, and your consciousness smooths them out. This has implications for what you are. You're not a thing, you're a process. You're a pattern of information flow, constrained by the speed of light and other physical limits, creating a persistent sense of self. The you reading this sentence is not the same you who started reading this essay hours ago. Not in a purely physical sense. Atoms have been exchanged, neural patterns have shifted, memories have been encoded. But there's continuity, causal continuity, governed by light-speed information transfer. Present you is causally connected to past you through an unbroken chain of physical processes. And future you will be causally connected to present you. This causal chain, respecting light speed limits, is what makes you persist as an identifiable entity. The speed of light doesn't just constrain what you can do, it defines what you are. You're a bounded region of spacetime, a localized information processing pattern that respects causality constraints. Your thoughts can't instantly influence distant parts of your body because signals take time to propagate. Your sense of self can't extend beyond the regions of space causally connected by your nervous system. There's a philosopher's thought experiment called the teletransportation paradox. Imagine you step into a device that scans your body atom by atom, records the information, and sends it to Mars at light speed. On Mars, the information is used to reconstruct you exactly. Are you the same person? From a physical perspective, the reconstructed you on Mars is causally continuous with the you on Earth. Information about your state was transmitted, respecting light speed limits, and used to create a new instance of the pattern. But it took several minutes for the signal to reach Mars. During those minutes, was there no you? Did you cease to exist and then begin existing again? Or were you somehow present in the electromagnetic signal? These questions don't have clear answers, because you is a higher level concept that doesn't map neatly onto the physical description. But what's clear is that any notion of personal identity must respect causal structure, and causal structure is defined by light speed propagation. You can't be in two places at once, except in the quantum sense of superposition for microscopic systems, because there's no causal connection that could keep the two instances synchronized. This connects to something profound. The speed of light creates individuals. By limiting how quickly information can spread, it creates boundaries around coherent systems. You're you, and not me, because there's no superluminal connection coordinating our brain states. Each of us is a causally bounded entity, separated by light speed limitations.